It is February 2026, and the James Webb Space Telescope has just shattered our understanding of the cosmic timeline again. For decades, we believed the infant universe was a chaotic, dark void that slowly woke up over a billion years. But new data from the edge of time proves that the cosmos didn't just wake up, it roared into existence with a speed that defies our standard models. The headline discovery is a galaxy designated MOMZ14, a name that will likely define astrophysics for the next decade. Confirmed just this month, its light has traveled to us from a time merely 280 million years after the Big Bang. This places it deeper in the timeline than almost anything we have seen before, existing in an era we thought was dominated by hydrogen fog and darkness. According to the Lambda CDM model of cosmology, a galaxy at this epoch should be a faint, irregular blob of gas, struggling to form its first stars. MOMZ14 is not that. It is shockingly luminous, compact, and structured. It shines with the intensity of a galaxy that has been evolving for eons, yet it sits in a cradle of the universe that should be barely active. The implications of this brightness are profound and disturbing for established theories. Spectroscopic analysis has revealed that MOMZ14 is already rich in heavy elements like nitrogen and oxygen. In astronomy, metals are the ashes of dead stars, meaning this infant galaxy has somehow already cycled through multiple generations of stellar birth and supernovae in a cosmological blink of an eye. We are calling this new paradigm accelerated maturation, a realization that the early universe was a chaotic engine of creation far more efficient than we dared to imagine. The gas clouds of the cosmic dawn didn't just collapse, they rushed together, ignited and enriched the cosmos with the ingredients for planets and life billions of years ahead of schedule. This acceleration isn't limited to single isolated galaxies like MOMZ14. In January 2026, Webb captured another impossible structure, a massive merger of at least 5 distinct galaxies occurring just 800 million years after the Big Bang. This is direct visual evidence that the cosmic web, the vast, invisible scaffolding of dark matter that holds the universe together, had already assembled into complex nodes. These new high-resolution, deep-field maps are finally allowing us to visualize the dark matter clumps that guided this formation. The invisible gravity of these clumps acted as the seed for the first galaxy clusters, pulling matter in with such ferocity that it allowed massive structures to stabilize when the universe was less than 5% of its current age. The existence of such mature structures so early puts immense stress on our standard timeline of cosmic history. Theorists are now scrambling to simulate how gravity could work this efficiently. If MOZ14 is typical, then the dark ages of the universe may not have been dark at all, but filled with a sudden, violent, and brilliant ignition of structure across the entire sky. To put this in perspective, imagine finding a fully constructed metropolis where you expected to find a few scattered tents. That is the scale of the anomaly Webb has uncovered. We are not just seeing the first stars, we are seeing organized, chemically complex systems that have no right to be this advanced, forcing us to ask if our clock for the universe's beginning is fundamentally misunderstood. The certainty of these findings comes from rigorous spectroscopic confirmation, not just photometric estimates. We aren't guessing the distance based on color, we are measuring the redshift of specific emission lines, confirming that this light truly left its source when the universe was a toddler. The data is robust, and it tells us that the early universe was a place of extreme density and rapid evolution. We are moving from a period of simple discovery to one of detailed characterization. We are no longer asking if galaxies existed this early, but how they managed to cheat the expected limits of gas cooling and gravity. The efficiency of star formation in MOMZ14 suggests physical mechanisms we have not yet accounted for, perhaps involving primordial magnetic fields or different properties of dark matter itself. This discovery is part of a larger pattern observed throughout late 2025 and early 2026. Every deep look into the abyss reveals a universe that is teeming with activity. The empty epochs are filled with light, and the chemical signatures of mature galaxies are showing up in datasets where we expected only pristine hydrogen and helium. But if galaxies were growing this fast, they must have had help. A galaxy doesn't just hold itself together, it requires a gravitational anchor, a monster in the dark to govern its rotation and feed its growth. We used to think supermassive black holes formed long after their host galaxies, slowly consuming matter over eons to grow to their titanic sizes. However, alongside MOMSY 14, Webb has spotted something else, baffling points of light that defy classification. We call them Platypus Galaxies, cosmic oddities that look like stars but act like monsters. In the next segment, we will investigate these strange architects and the supermassive black holes that were somehow already giants at the dawn of time. The architects of the cosmic dawn are proving to be far stranger than any simulation predicted, and the most baffling among them were only identified in the data from January 2026. Astronomers analyzing the latest deep field surveys have stumbled upon a class of high redshift objects that defy the standard laws of galactic taxonomy, earning them the eccentric nickname Platypus Galaxies. To the eye of Webb's near-infrared camera, these entities appeared deceptively simple, manifesting as tiny, unresolved points of light that look indistinguishable from solitary stars sitting in our own Milky Way foreground. However, when the telescope's instruments dissect their ancient light using high-resolution spectroscopy, the data reveals a dual nature that is physically difficult to reconcile under our current understanding of physics. The spectral lines exhibit the distinct calm thermal signature of a densely packed stellar nursery, a region where thousands of suns are quietly igniting, yet this is overlaid with the violent high ionization signature of a shrouded supermassive black hole. They are a hodgepodge of features that shouldn't belong together, simultaneously a calm stellar womb and a ravenous gravitational engine, forcing us to rethink how the first massive structures assembled in the dark. While the Platypus galaxies represent a mystery of classification, another heavyweight discovery has settled one of the longest-standing debates in astrophysics, the chicken and egg problem of galactic formation. For decades, the standard lambda CDM model assumed that supermassive black holes formed slowly, growing from the seeds of dead stars over billions of years, appearing long after their host galaxies had stabilized. The confirmation of the object known as Canix-LRD-Z8.6, observed existing just 570 million years after the Big Bang, has violently overturned that gradual timeline of cosmic history. Webb's instruments have confirmed that this supermassive black hole is already a titan, possessing a mass that the limits of accretion physics suggest should be impossible to accumulate in such a short window of time. Its existence at such a primitive epoch provides the smoking gun for the theory of coevolution, demonstrating that the monster and the galaxy grew in lockstep, rising together from the primordial gas. Rather than being destructive parasites that arrived late to the party, these primordial black holes were likely the gravitational anchors that accelerated the assembly of the cosmic web far faster than dark matter models predicted. This fits the terrifying pattern of accelerated maturation defining the 2026 data, where the early universe was not a chaotic soup, but a highly efficient engine building structure at breakneck speeds. But these heavyweights were not just piling up mass, they were also driving the extreme energetic processes required to forge the universe's first heavy elements, seeding the cosmos with potential. In the next segment, we will analyze the chemical fingerprint of this era to reveal how the ingredients for life appeared billions of years ahead of schedule. The universe wasn't just becoming massive and luminous in its infancy, it was becoming surprisingly complex. For decades, we believed the cosmos spent its first billion years as a sterile factory of simple hydrogen and helium, incapable of forging the delicate carbon chains required for biology. But the infrared eyes of the James Webb Space Telescope have just dismantled that assumption with a single precise spectral reading. Focusing on the ultra-luminous galaxy IRAS 0725102448, astronomers have isolated a specific chemical signature that shouldn't be this distinct in such a high-energy environment. For the first time outside our own galactic neighborhood, Webb has confirmed the detection of the methyl radical, a highly reactive organic molecule that acts as a critical stepping stone for building larger, more complex hydrocarbons. Finding it here is like finding a bricklayer's trowel in the ruins of the very first city. This detection is not an isolated anomaly. It is part of a staggering pattern of accelerated maturation that has defined astrophysics in early 2026. Alongside the methyl radical, the spectral data reveals unmistakable traces of benzene, a ring-shaped molecule that serves as the backbone for a vast array of organic chemistry. The presence of these compounds proves that the prebiotic ingredients for life were not late arrivals to the cosmic party. They were being cooked up in the chaotic, radiation-blasted nurseries of the early universe, billions of years ahead of the timeline predicted by our most optimistic astrobiological models. To create these heavy elements so quickly, the first generations of stars must have lived and died with ferocious speed. They burned through their fuel, went supernova, and enriched the interstellar medium with nitrogen, oxygen, and carbon in a cosmic blink of an eye, seeding the void with dust. This chemical cocktail suggests that if a habitable planet could have formed in these ancient epochs, the molecular toolkit required to jumpstart biology was already waiting in the dust clouds. The universe was chemically ready for life almost as soon as it was physically able to support stars. But complex chemistry needs a vessel, and structure needs a blueprint. This brings us to the final piece of the 2026 puzzle, the invisible scaffolding that held these early chemical factories together. We have known about dark matter for decades, but we have never seen it like this. Utilizing the deep field surveys completed this February, researchers have constructed high-resolution maps of the dark matter distributions surrounding these ancient galaxies. These maps reveal the hidden architecture of the cosmic web, assembling much faster than standard dark matter models predicted. We can now visualize the massive invisible clumps of matter that acted as gravitational wells, pulling in the pristine gas to ignite the first star clusters. This wasn't a slow, random accumulation. It was a rapid, guided construction project that built the skeleton of the universe in record time. The discovery of the MOMZ-14 galaxy, the Platypus objects, and now this complex organic chemistry all point to a singular, uncomfortable truth for cosmologists. The lambda CDM model, our standard theory of the Big Bang, is under extreme stress. The universe did not wake up slowly, it snapped awake. We are no longer just discovering dots of light. We are characterizing a mature, dynamic, and chemically rich environment that existed when the cosmos was just a toddler. The Dark Ages were not dark. They were blazing with creation, mergers, and the forging of the very elements that make up your body today. As we move further into 2026, the question changes from how did galaxies form to how did they grow up so fast? The James Webb Space Telescope has turned the lights on in a room we thought was empty, revealing a history more vibrant than we ever dared to imagine. The era of simple discovery is over. The era of rewriting history has begun. If you want to stay ahead of the rewriting of the cosmos, make sure you are subscribed to QuasarQuest. We will be here to break down every photon of evidence as humanity peers deeper into the abyss.